impossible to do 100%, but come closer to that. So we have worked on corn over. It can be other grass also or wood also. We developed a biorefinery concept. This was funded by Department of Energy, DOE, and I will show you what we did. A lot of work there, so I try to summarize here. The concept is corn over, treatment, hydrothermal liquefaction, char, aqueous waste, heavy bio oil. From here, char we made biocarbon. We use that biocarbon from the nanofibers. Aqueous phase had a lot of phenol because it has very green. We saw that you can recover phenol from it. Phenol is a bulk chemical used for many other things. So if the industry is just worried on phenol, they'll focus just on that. But you have used for other components. Lactic acid, we showed that you can recover from aqueous phase because it's high in lactic acid. So it depends what we want to make, we can do that. And then the leftover material can go hydrothermal and we can make heavy bio oil for fuel applications. So the concept we propose is a team project. We were part, my group was part. South Dakota State University, they were leading in that, but we are ready. Virginia Commonwealth University, then National Lab was there, Idaho National Lab, and South West Research Institute. So the concept was, we will take cornerstone as it is never good, you have to do something. Alright? So we did pre-treatment, alkaline pre-treatment. You do hot water, but add some alkali to it, means for the pH. Keep the pH around 6 to 7 or 8 in that range. For that we add potassium carbonate and do pre-treatment, so you get two phases. What pre-treatment does, if you do aqueous, you have a water phase, it will solubilize hemicellulose or lignin and other things, and you will have a solid phase which is broken, higher surface area, good for enzyme. Right? So the solid, we did touch one because you know this is good for enzymatic hydrolysis. So we did hydrolysis, we didn't do fermentation. Hydrolysis will give you sugar can be fermented, we didn't broaden our scope in that side. But when
solid fermentation or?
Yes, so we got two phases. This is solid, this is liquid. So this is pre-treatment done, so it's a porous material. Then subject enzyme, you can release sugar. Alright? Once you release sugar, you can do fermentation. But that's not our area, so let it go. But once you release sugar, the leftover material rich in lignin, alright? So that solid, we talk about this side, but the pre-treatment when you do aqueous phase, hemicellulose mostly. But if you do pre-treatment around 200 degrees Celsius, 180 degrees Celsius, think of a hot water treatment with little alkali in that. So the liquid phase has hemicellulose, some lignin. And we did air oxidation of that, wet oxidation of that, and we could get polylactic acid or phenol. Okay? In solid, if you want to make ethanol, remember any process you do, you end up getting some solid ethanol. Alright? It's never entire being one component. You have gas, liquid, solid. You do enzymatic hydrolysis, you will have some unhydrolyzed solid which cannot be hydrolyzed. And this is bait, but when you do hydrolysis and all this lot of water. So this bait solid we did hydrothermal with that. With hydrothermal, you get the oil. So yeah, with hydrothermal, you will get oil, maybe bio oil. You take it out. Then aqueous phase is a lot of phenol and lactic acid. So we took out phenol separated, we can show that. We took out the rate oxidation and you can oxidize with lactic acid, we got lactic acid. And the solid after hydrothermal, heavy bio oil, then still you left it char. That char will make biocarbon and carbon hydrogen. So the cornerstone biorefinery concept is sold. You can make these many products from cornerstone. And we started with just water here, little alkalinity. Then hydrocarbon, just water. Wet oxidation, water plus oxygen. So closer to green and sustainable processes, not much harsh chemical, and we saw that these things can be made. Now industry has to pick up which one they want. They have the money, they have the techno-economic. We did the techno-economic analysis, life cycle assessment under this project. We developed pilot scale facility at South Dakota, 1 ton per day. Hydrothermal reactors we developed and collaborated with National Lab, Oil Lab and other integrated process. And this year is ending this project, but for the last 5-6 years we worked on this. So at lab scale, at pilot scale and integrated. How we made carbon nanofibers, we had expert on that. We get that biocarbon what we made and they use and other things to make carbon nanofiber. Lactic acid being so that how can at aqueous stage and get oxidation, you can get good quality lactic acid, can be separated. And lactic acid used for polylactic acid, PA. You can polymerize it, PLA, and then you can make biochemical plastics. Labulinic acid is another platform chemical. So there are certain chemicals which are called platform chemical because you can do so many other things with that. So cornerstone acid treatment, little acidic conditions, we said that you can make labulinic acid. So all these things what I am saying they are published. So if you are interested in certain thing and you can share the paper or we can discuss it on that. Biocarbon we need for energy storage purpose, right? Supercapacitor and other things. If you look at energy storage, supercapacitor fits here. Again energy thing, watt hour per kg versus watt per kg here it is. So we need lot of electrode material here and biocarbon can be a renewable source or renewable carbon for making that. The oil quality which is lignin after treatment, we turn into hydrothermal, you can get this kind of oil. They are not ready for final period, but these are biofuel which needs upgradation. Remember hydrogen, you can do hydrogenation and activated carbon. Maybe you can stop now and I will talk about that. Okay, let's just keep going. So today's first session was application of captured carbon and renewable energy. And I showed you through LG how it can be done, right? The next one is this one is environmental and economic implications of CCU. And I already started discussing about that. If you don't realize, I'll bring you back to the biorefinery concept. So biorefinery concept will bring you economic. If you are looking at one product from feedstock, it requires support from other byproducts also. Otherwise, difficult to gain economic support. Okay? And environmental anyway we are all the throughout we are addressing the waste and circular and other things. So definitely we are working on that. So I will continue carbon capture utilization, environmental impact and economic implications through multiple product development. So I have been saying that no matter what process you do, you will end up getting some process residual in organic waste. You try LG, you try biomass, you try organic waste, make ethanol, then be residue. That's another source of carbon for materials. And I am showing you some some examples how we do that, and there are multiple ways to do that. So activated carbon, how many of you know about it already? If you know water treatment, activated carbon all around there. If you are on air filtration, you know that activated filtering material. Okay, it's a huge application. And if you get into these applications, impacts are bigger. If you are able to replace activated carbon with certain food waste and all, you are tackling such a huge area. So can you make activated carbon from those residue? Let's say you made J12, you made extraction and all those things. The residue which are left over or entire without making even the residue, can we make activated carbon? So for making activated carbon, we need to know what is activated carbon and how it is made correctly. So, activated carbon is known to surface area porous, a sponge character. A sponge you can squeeze. This is hard material, you cannot squeeze, but you have a contours, lot of pores inside, where it traps molecules. It has many different applications. Electrodes, graphitic material, there are many different applications. So, can we bring renewable carbon? What is the application? Currently we get from coal or coconut shell. If price is higher than normal things because you do activation and other things, it's a costly material. Typically it's done at high temperature, carbonization, steam activation, and it is sold in form of pellets, depending on what application you are looking. It is sold in form of powder and it is sold in form of granules. So this in short we will call it GAC, pack, or powder. Coconut shell and coal are the major things. Coconut shell is still fine, it's renewable, but mostly it is made from here. You get better quality. So coal replacement is through renewable carbon we are talking. And I will show you some example what it is and lot of work going on, so we will try to connect how it works. So this material is from bioethanol plant. You make corn, sugar, ethanol, bioethanol, cellulosic ethanol. You do an enzymatic hydrolysis, fermentation. The residue in fermentation crop is this material, which is mostly liquid. Some enzyme and a microorganism mixed into it. Yesterday I was talking that this material is typically burnt. Okay? Bagasse burnt for heat. This is bioactive. It came from fermentation to other things. And handling it is issue because fermentation residue is a lot of water and other things. So we did carbonization, hydrothermal carbonization on this because you don't have to dry. We get hydrochar and then we took that hydrochar, we activated it for high surface area. This is one of the only work in 2013 or 14 we did. And I cannot say we were the, but we were among the only ones.
Hydrocarbons, is it kind of water inside? There is moisture.
Hydrothermal?
That is what we were saying, hydrocarbons.
Hydrothermal carbonization. So hydrothermal process, you can do liquefaction, you can do carbonization, changing the temperature condition, time condition. In one time, hydrothermal means water at temperature. In one time, you are looking to make oil. Okay. Even if you are making oil, you are giving residue with hydrochar. Another time you think this is not oil industry, I want more carbon. So you are doing tuning such a way that you make more carbonized material. Okay, so residence time is little longer, low related carbonized. So here that was focus was carbon. You can do hydrothermal liquefaction and get oil, but the focus was can we use as a carbon material for activated carbon. So we did hydrothermal carbonization. Again cooking, pressure cooking, little longer time, you can use catalyst, no catalyst, you get carbon material. And then this carbon, this one is fermentation residue, we did hydrothermal carbonization plus activation to make more porous, like activated carbon is made. So we try to do that. So activation temperature, we tried this research studies, we tried different temperature, activation time, different time. We impregnated with potassium carbonate here, zinc chloride, potassium carbonate, and phosphoric acid. We tried to do other impregnation thing and we heated at different heating rate, and we saw that what kind of carbon we are getting. And are they good, as good as activated carbon or not? So, summarizing the result with a good result we are getting, others where I am not discussing. So, zinc chloride activation work. You see the commercial activated carbon and zinc chloride activated carbon, what we did in lab. You will see that many of the property, most of the property is matching or data or close to that. And it was published. Phosphoric acid didn't work well, surface area was less, but here in the 1000 plus in activated carbon. We did for dye cleaning as a test. Normally for basic starting point when you use any adsorbent to try to see if it is good for dye or not. So that was the thing. So it is as good as very close to commercial application. We saw that we just manage that. This is published. So this can be done, activated carbon can be done. Okay. If you are looking at electrode material, this is a carbon. Maybe you want more porosity, maybe you want full doping, and you are looking at capacitance valuable nodes, so you can use that. We have that also. But this is where we started in 2013, this was work. Other thing we did, this was a Department of Agriculture project. So how much lubricant we use? Have you ever thought? Lubricant. You know lubricant, am I right? Bearing lubricant, everywhere we use. So much, alright, everywhere you need any machine, you need lubrication. So it's again commodity kind of thing. If you change that, you have an impact. And how lubricants made? Anyone? How do you get lubricants? How is it produced? Current in the market when you buy lubricant, how it was produced? Yeah, so it comes from oil refined itself. Okay? So lubricants again, petrochemical business. Can we make bio business, bio lubricant? Okay? So if we replace even partly, it's a bigger impact. So we tried that under Department of Agriculture project, and again we focused on ethanol plant because that is coming up. So residue, what to do? People don't know. Good use of residue material besides burning it. So we thought let's try lubricant. So this is an hydrolyzed solid, the picture you saw that for activated carbon. We took this time we didn't do carbonization, we did liquefaction. Because lubrication we did oil kind of thing. Okay? So in a hydrolyzed solid, and we took bleach, this cooking oil, and we made it biodiesel from that, and then unhydrolyzed solid and oil, and we combine them together. Okay, it becomes more like a lubricant, kind of biolubricant. So the approach is you take unhydrolyzed solid, this is one base material, and you need hydrothermal liquefaction. Again, you will get some charge because you get residue. Bio oil, and then you have biodiesel from waste cooking oil. You brought LCIS and some chemistry we did, and then hydrodeoxygenation. This was done by Montana State University, this one is done by us, and it's the integrated product. And we got a chain which is called biolubricant. So again, few papers are on that for details, but we showed that this can be done. Now, economics, other things are part of it, and the researcher we try to see this can be done, and then how can we improve on that. So cornerstone we talked, LG we talked. There is another residue sitting somewhere. We don't see much. It's seed. Alright? We press it, we take oil, the cakes goes for animal feed, but all cakes cannot go for animal feed because some are toxic.
Even moringa.
Yeah. Anything. So oil seeds, these are all number how much they are and all. The process continuously. What is the process? You pour it, clean it, decortication, open up, milling, grind, oil expelling, pressing, crude oil and cake. It's a good cake, animal feed.
So do we use a common process like soft slate extraction, or you don't?
No, this is industry I'm talking about. They press it typically.
Press it.
And from cake, leftover oil, they use chocolate extraction, hexane, and they get some additional oil before throwing it. And then that goes for animal feed if it is a good quality. But if your seed is some toxic like jatropha, don't put cake for animal feed. Okay? So this is conventional process. So they both are cleaning, decortication, milling, grinding. Sometimes they do solvent extraction to recover more of oil. By pressing you can get so much, then leftover you do extraction. So but we change the approach here. Again we propose how to do that. Take oil seed directly. Don't worry about too much cleaning and decortication and all. Take as it is. Put in hydrothermal water. Again kind of cooking. Okay? We call it pre-treatment, subcritical water pre-treatment. So when you do this pre-treatment, you generate two things. This water you generate water phase and the solids. The solids are seeds which have more porosity now. They are not broken. Treatment we did there so that they are not fully broken, it's still solid. But their cover is kind of more surface area. So the first phase is solid, where your oil is still there, but the layer or covering layer is much bigger now. Now you can do soft extraction on that. Versus soft extraction here. This needs to be, this one is ready, you can after in extraction more efficient. So this benefit you see. When you do the cake, oil gone, finished oil you can do for fuel or whatever application. The cake is wet now because you need hydrothermal. There's a lot of water in there. But some impurities and the water came out here from pre-treatment which dissolved something from the copper and all. It has dissolved organic compound. And cake here with hydrothermal carbonization. Sometimes it's called subcritical water carbonization. Kind of then pre-treatment just some carbonaceous material and other things dissolved, cleaned up basically seeds. And then cake coming from this side. We did hydrothermal carbonization and we made hydrochar. Okay? Now you remember if you have hydrochar, you can make activated carbon. High surface area carbon material, electrode material. You can do so much with carbon. Right? This is renewable carbon, we got it. Oil. We say that this can be another alternative method where we develop more high-end product instead of just cake. And then we are the chemicals, just water, alright? And soft extraction, if you do that, it can be done with ethanol, milder solvent. You don't need hexane. You need hexane for where you have to don't have porosity and all it, but it's much more milder solvent, so you can do green solvent. This we had a patent file on that and then published also after that. So method and application, you can see that these are the sample we generated. We tested many different seeds, cotton seeds, many different seeds. I don't remember all of those. Canola seeds. So we extracted, and one question will come. We did hydrothermal pretreatment, did you change oil? Right? So first we look at ECMS diagram. You will see that it will change pretreated seeds and the conventional seed which you ground and from that extraction. One thing we did mention, the seed when you use it for hexane extraction, you have to ground it for the surface. It didn't do the grounding. And the oil quality is not changed. Extraction efficiency of pre-treated seed is gone so much higher versus conventional canola, mustard, flax, cotton. We didn't have many seeds. In fact, with tobacco company, we had their seeds. The mass balance, material balance, that's what I was talking yesterday. Any process you do with the box and what came in, what goes out, and what is the price for this side, that side. So we did that, techno-economic and other things. And hydrochar, how much you can produce, oil, how much produce. This is a feedstock for carbon material now. Oil is feedstock for fuel or whatever applications. Municipal solid waste. LG we touched, lignocellulosic we touched, oil seeds we touched, another one is food waste, municipal solid waste. So municipal solid waste we developed a concept. This 4.9 is pounds per capita waste per capita waste, which is a lot. Here may be less, but we may not be keeping track here. So problem statement, and you see that most of the things goes to land filling. Okay, these are organic waste goes to land filling. Some goes for incineration. Incineration also is environmentally not very friendly. Lot of emission gases comes out. Little goes for composting. Metals goes for recycling. You can separate that. So that's a general practice. What they contain municipal solid waste. This is representative from US municipal solid waste. You will see lot of paper, which are similar to many other ones also. Mostly papers, which can be used. Sticks, metals, food, next food component of municipal solid waste. Yard trimming, grass, yard trimming, clean with that. So these are all organic. And they have potential to stock for what we are talking, multiple products, and support the economic growth and environmental issues can be addressed of land filling and other things, right? So again we went to the carbonizing the food, so that we are worried about carbon, how can we cover? That's the key. Carbon can be biogas, can be hydrochar. We looked at hydrothermal carbonization, take all the waste. So municipal solid waste can do as it is, or if you segregate metals and all, it's better. You segregate it to the hydrothermal carbonization, and there are European companies, at least 5 or 6 I know, they are doing hydrochar production from municipal solid waste or food waste and all. Even China has got many units they are developing for hydrochar at industrial scale. Because what it requires waste and water and heat and charcoal to get the product. So the hydrochar, which is a renewable carbon, it can be green coal also, and blend it with coal. Alright. Europe and United States or Canada need a lot of heating. Wood pellets exported from here, African country goes to Europe. This is another pellets, which can be done from waste, and so it's a green coal. Because I was talking water and gas, this is the composition normally. 5 large plants in the world are known, and how much coal and other things you get. So one of my PhD students graduated, came out with this concept, we did that. Can we integrate this with the question comes aqueous phase when we get, what do we do with that? can go to wastewater treatment, but we lose some carbon on that. So what we propose the hydrothermal carbonization, get hydrochar, and that's energy or materials application for activated carbon. The aqueous phase, and COD, right, your organic carbon, you can put in anaerobic digestion. You can blend it with the existing feedstock, or you can have a liquid anaerobic digestion. That will be fast, so you can make biogas. Now we want to supply it for HPC. This can come to the end of a closed circle, and you will recover carbon, energy, or materials. So we did publication there and others there, and the solution is started from here, which way MSW is getting that. It hydrothermal carbonization, liquid digestion, liquid digestion. So this is faster than the solid digestion, right? And we had biochar or hydrochar particularly. Now the material balance looks like this. You can get at least 1/3 of carbon. Weight wise, percentage wise is more, but carbon percentage is more. Other thing we have been working, and again it's a future direction, because of electricity, most of the chemical reaction focus is shifting towards electrochemical, because electricity availability is getting better, renewable energy, solar, wind, offshore farm and all coming up. So what you can do with heat, you can do better with electricity. Remember, two kinds of heat source. One is low quality, another is high quality. Heat is low quality because you have lot of loss. Okay, it's like the stove cooking with wood or coal versus electric heaters. Here you can convert almost anything. So that's why electricity driven processes are getting attention, even refinery and other processes here we can do electrochemical. So electrochemical hydrogenation is done for many things, because hydrogen efficient compounds are a lot. So we try to look at renewable electricity, oxygenated compound, bio-derived oxygenated compounds can be made hydrogenation out of it. So we tried acetone and furfural, we showed that this can be done. Why acetone and furfural? Because when you do pyrolysis, these compounds are present in oil. Okay, if you do hydrogenation of those, they become stable, or it can be a different compound which can produce products. This is typical composition, and you see furfural here, good percentage. So can we use that? Fuel alcohol can be made. The benefits of electrochemical hydrogenation or oxidation also is mild condition. Hydrogen source can be water itself. Carbon recovery is high, you can do that. Selectivity is better. Challenges are lower than solubility in aqueous solution and those kind of things. Becoming attractive because of electricity availability. Thermal processes are proven, done for a long time, but efficiency wise is getting better on difficult action. We supply hydrogen gas for hydrogenation. There we are trying, can we do hard electrolysis, can contribute to hydrogen production also from water. So bio-derived compound, this we developed electrolysis we have, and we tried to do that, and that was the work we finished. So this is all on lignocellulose biomass and using hydrothermal processes. These are the products, funding and heat and other things. I try to connect this with team here, carbon capture, utilization, and how you can do that. The take-home message is you can still stay green while designing your processes. Water is good enough, get unique life, and we can use for multiple products. The concept platform, I said flash hydrolysis, that concept can be vaccination in different areas.